In this video, we're going to use the exponential growth and decay models to find values other than the resultant value. It says researchers recorded that a certain bacteria population declined from 750,000 to 250 in 48 hours after the administration of medication. At this rate of decay, how many bacteria will there be in 8 hours? Round to the nearest whole number. So I'm going to put our formula that we're going to use up here, which is the exponential growth and decay model. It's basically the same as like the continuously compounded model. Obviously, bacteria are going to grow all the time, so that's why we're going to use the Euler's number in our formula instead of using like the compound interest formula where you have a certain amount of compounded interest per year. This is always happening, so bacteria is always growing, so we got to use this model. You can see they're the same equation. You've got P of O as a starting amount. Well, that's the principal in this equation. You've got K as the decay growth or rate. That's the R in this equation, right? So the same, they're just different variables standing for the same thing. T is time in both of those. And A is the amount that you end with. We'll put that up here. A is the amount that you end with, and P of T is also the amount that you end with. So they're basically the same equation, just with different variables. So let's write down what we know. We know that P of 0 is 250. And we know P of T is 750,000 bacteria. We know our time is 48. Now that's for the first problem. That's one thing to acknowledge. This is the first problem. We want to know how much, so this is a K value, not the R value, but what is the rate? So what is K? Once we find K, then we can solve the second problem. For the second problem, we know that the P of 0 is 250 because it'll still start at the same amount. And we know that the time is going to be 8 hours. But we don't know the K value, and we also don't know what P of T is, which they're going to ask us, what is P of T? So the first thing we need to do is solve for the K value, then use that K value in the second piece of the problem. So we'll start by plugging in what we know. We have 750,000. I'll just kind of write that over here. 750,000 is equal to 250. E to the time, 48. Okay. And then I'm going to divide by 250 on each side. So 750,000 divided by 250 is 3,000. E to the 48K. Take the natural log on both sides. This is going to cancel the natural log E. The 48K comes to the front because of the log laws. And so you're left with natural log of 3,000 equals 48K. And then we're going to divide by 48. And so we're going to write our K value right here. Now I'm not going to use this K value. I'd probably just leave it in the calculator, but we can type it all in. So I'd have natural log of 3,000 divided by 48. And I'll just leave that number in the calculator. That's my K value or my rate, which is 16.6%. So I'm just going to write 0.16. Let's round that to 7 just for right now. But I'm going to use the whole number when I solve the problem. So I'll use this while I'm doing the algebra. That's going to be what's plugged in. So K is actually equal to 0.167, which means our K value here is 0.167. So then I'm going to take and plug all this into this formula again. We have P of T is equal to 250 E to the K value, which will be that 0.167 value, and then I'm taking that times 8 as well. But I'm not going to use 0.167. I'll just use this value. So I'm going to put this up here and take it times right away 8. And then I'm going to use the E button and take it to that answer. That way I'm making sure I'm using the whole number the whole time. And then take it times 250. And that tells me that my bacteria after 8 hours would be 949. And what do they say? Round to the nearest whole number. So 949.